Okay, so, because that's what I'm for. Let me, say something. Oh, yes, and also, I'm teaching commutative algebra apparently in the fall, which was very thrilling. Love to have you. So if you've got any questions about the course, just give me a holler. Okay, so let me say something about the next, homework assignment. Well, I think flagging before McHenry will soon better days. Okay, so, the first problem next time, this is kind of I like this problem, it's kind of fun. Suppose you have, F, field extension of K, and you have some algebraic element U and F, and it's algebraic of odd degree. And what I mean by that is if you take the minimal polynomial of U, it's of odd degree. Then show that K adjoined with U squared is equal to K adjoined with U. One containment is obvious and it's true in all cases, right? But the interesting part is K is actually contained in U squared. And then what can you say if U is transcendental over K? And you might ask yourself, what can you say if it's of even degree as well? Number two is a fundamental kind of question for lots of things. This is important in coding, studying finite fields, et cetera, et cetera. Here's a general statement. So if you have a field, and of course, if you throw the zero out of the field, then you've got a multiplicative group, right? Suppose you have a finite subgroup of that multiplicative group, right? For any field. Show that if G is in fact a finite subgroup of the field, then G must be cyclic, right? Which is kind of cool, which means that if you look at, basically, if you look at any finite subgroup, multiplicative group of the field, it has two roots of unity, essentially. Number B, show that if F is finite, and this is wildly untrue in general, show that if F is finite, then the product of two non-squares in F is a square, right? Now, I don't know much, but I know that 2 is not a square in the rationals, and 3 is not a square, and 2 times 3 is still not a square. However, for any finite field, the product of two things that are not squares automatically becomes a square, which is kind of cool. And finally, this is important again in number theory and a number of other things. If F is finite, show that every element of F is actually the sum of two squares. Again, this is not true in general. Look at the real numbers. No negative number is the sum of two squares. Okay. Right. Number 3. Suppose that F and K are fields, and F is algebraic over K. So you, by the way, doesn't even have to be finite. It just has to be an algebraic extension. Show that any integral domain that you can jam in between K and F has to also be a field, right? So if you've got an algebraic extension and you can put an integral domain between, that integral domain has to be a field. Number 4, suppose K is a field and U and V are elements of some field extension of K, and U and V are both algebraic over K. Show that if the degrees of U and V are M and N over K respectively, and again, what I mean by the degree of an element is that is the degree of its minimal polynomial. Then the degree of K, U comma V over K is less than or equal to Mn. We discussed that a little bit. And show that equality holds if the greatest common divisor of M and N is 1. So if M and N are relatively prime, then you get equality there. Now, I notice I do not say in this problem if and only if. And finally, find all the automorphisms of R that fix Q, right? We talked about the Galois group last time, right? What's the Galois group of a field? What that is that's the group of automorphisms of the big field that fix the little field. What happens here? My proof almost looked like I was doing some analysis, but a little analysis.
Ordering, right?
What's that?
Yes, use the ordering.
I'm not gonna say you're gonna have to, because there's almost always more than one. Let me say that I use the order, yeah.
I'm pretty sure I did something like that in algebra one.
It's very interesting, because we're going to see that, there's lots and lots of automorphisms. But here, you will get a surprisingly small answer. Okay, any questions? Okay, so, yes, we're gonna get to some cool stuff. Last time, we talked about, the Galois group. Uh, uh, This is just the group of automorphisms from F to F that actually fix the base field K. So. Let's let D be a square free integer. This, in case you're not familiar, what this means is the only square that divides this integer is one, right? So 12 is not square free, but -1 is, for example. Actually, we're going to need something. There's an important observation. So here's an observation. Suppose sigma is in Galois group. Okay. So I want you to get used to that terminology. That just means sigma is an automorphism of that. Okay. And suppose U in F is algebraic over K. Okay. Then if F of X and K of X has U as a root, then sigma of U is also a root of, right? So if you have any root of a polynomial, say U and F, then its image under sigma also has to be, and the proof of this is not too bad. So let F of X in polynomial. Well, the fact that U is a root, this means now apply sigma in a different color to both sides of this. If you apply sigma to this, then of course sigma is an automorphism and it fixes K. So liberally using the automorphism property. Of course, sigma 0 is 0. So notice that and that's an incredibly important observation. So let's get back to this. Let me point out that what's the degree of this extension? 2. It's degree 2. And in fact, it's got bases. It's got many bases. But that forms the basis of the vector space, right? Now, to understand an automorphism here, really all I got to do is just got to tell me where the basis goes, right? So, and of course, D, radical D, is root of. Now, because of the fact that I've demanded that D be square free, it's easy to show that this is an irreducible polynomial, right? Look at sigma radical D. It can either go to itself, it can either go to itself, or it can go to the other root. Are these distinct? Yes, they are, because my characteristic is not 2. And so actually there, and you can, of course, this gives rise to the identity automorphism, and we don't need to check anything there. And this is sometimes called conjugation, right? Back in the days when you were rationalizing denominators and so forth, when you were in high school, your teacher probably didn't tell you this, but this works out very well because it's an automorphism, it's square root business. So you actually have 2 automorphisms, the identity and the conjugation automorphism. And of course, notice that when you apply the conjugation automorphism twice, it gives you the identity automorphism. This is isomorphic to C2. Okay. Okay, what about this one? And this will be kind of a interesting foray into the next one. Well, how about this one? Anyone want to guess this one?
C2 some, C3 some C2.
That would be my guess, right? Because this is a root of x squared minus 2. This is a root of x squared minus 3. You can probably swap out. Are they independent? They are here. This is actually isomorphic to Z2, Z2. Let me point out that this example is just intuitive at this point, but it seems like you should have basically an automorphism that swaps this with its negative, an automorphism swaps this with its negative, and then kind of the sum of those. It should be Z2, Z2. How about this one? Oh, was it?
Oh, so can you just briefly explain again why you shouldn't expect to be able to send the roots to anything else other than other roots of the same?
Well, that we don't know we can send it to every root, but we know that if you have a root, it has to go to another root because of the fact that it's an algebraic element, right? Because if you look at radical D, if U is, so suppose sigma is any automorphism. Well, then sigma takes radical D somewhere. Now notice that radical D squared minus A is 0. Right? Because, yeah, you're right, you freaked out about that. There, that's better, isn't it? Right? So if I apply sigma to this, let's just be careful about what we do here. This is certainly sigma radical D squared minus sigma of D. And of course, the other side sigma of 0, which is 0. Now sigma fixes D, because remember sigma is an automorphism, fixes the base field, which D is in Q. So, and this, because of the fact this is an automorphism, this is sigma radical D, sigma radical D, which is sigma radical D squared. So wherever the sends radical D has to also be a root of that same equation. And so you can only send roots of algebraic equations to other roots, which is, and that's extremely restricted, right? And that's why that's important. Here's one more example before I go through a rather in-depth one. Why is that?
The other groups, some of that too.
That's right. Right. Agree. Other roots. Omega cube root of 2 and omega bar cube root of 2, where omega is the primitive cube root 1. Am I okay with that? Now, an element of this, notice that 1 cube root of 2 and cube root of 4 is a basis for cube root 2 over q. This extension is of degree 3 because x cubed minus 2 is an irreducible polynomial. So it's got that basis, right? Notice that the last basis element is the square of the first, or the last is the square of the second. So really all I need to specify is where does this go? Then sigma of cube root of 2 must be cube root of 2, omega cube root of 2, or its complex conjugate. Agree? It's got to go to another root. But it can't go to these two. Why not?
Because they just belong to.
That's right, they're not even in here, right? They're not real, so they're certainly not in here. So your only choice is to send this thing to this. But once you fix that, you fixed everything. Right, so the only automorphism here is the identity. Right? So this brings me to the first example. The reason this example was kind of disappointing is because this animal had no place to go, right? Only to the real root. What if we make a field a little bit bigger? So let's consider the following example. Consider Q root 2 omega. And this I will probably sometimes call cube root of 2 alpha, so I don't have to do this, write it out all the time. And omega is let me point out a couple things about omega that will be useful. The minimal polynomial for omega is this quadratic polynomial. You can check me with the quadratic formula on that if you like. So in particular, omega squared is -1 minus omega. And this is also equal to the complex conjugate. So when you square omega, you actually get its complex conjugate. Okay with that? That'll be useful for us, I think. Now the roots of x cubed plus 2 are alpha, alpha omega, alpha omega squared, which is alpha omega bar. So notice that all three roots of this are actually contained in this field. This is the smallest field that contains both the cube root of 2 and those other pesky things. By the way, any guesses as to the degree of this extension? Over Q. I would agree at 6, right? Everybody agree that if I go this far, I've gone, in fact, I think I'll do it. What's the degree of this extension? It has to be 2 because Q alpha is real and omega is not real, right? Omega is a root of a quadratic polynomial over Q, so it's a root of a quadratic polynomial over this, and it can't be a root of a linear polynomial over this, otherwise this wouldn't be real. Right, so this has got to be 2, no other way about it. And the degree of this is 3, because x squared minus 2 is irreducible. This is a 6th degree extension. So I'm going to make a table here. And if we understand this table, I think it'll be a big, I'm oversimplifying here, but a big chunk of the fundamental theorem of Galois theory will be contained in this example. As it turns out, let me write down kind of the basis I want to use. 1 alpha squared omega alpha omega alpha squared, I guess. Yeah. If you bother to do it, you can prove that these are linearly independent elements and they're a vector space. They generate a vector space here. Now, what I want to do is I want to I want to figure out what every automorphism. I want to try to figure out what all the automorphisms are and what they do. Now, how many roots are there of x cubed minus 2? There's 3 of them, right? Yes.
I have a question. The homeomorphisms we are considering are of Q modules or of fields or?
Yes, they're both. The automorphisms are ring automorphisms, they're field automorphisms for the big field.
Okay.
But as a Q vector space, there are also vector space homomorphisms over Q. That's why the Q is fixed. You can pull Qs out of it. Right? So, in other words, what will happen here is the way the automorphism works is for all U, V, and F, sigma U V is sigma U, sigma V, just like a ring homomorphism. But if U is in K, the base field, then sigma U V is U sigma V. But since the base field is fixed, notice this is also sigma U sigma V. So there's no inconsistency here. It's just that U and sigma U happen to correspond if it's in the base field. Right. Does that answer the question? Okay, so I've got 3 roots. Alpha, alpha omega bar. Right? And let's see here. All these roots, just a shortcut. This is root 1, root 2, root 3. Somebody tell me why the Galois group of this field extension, the number of automorphisms in this group is no more than 6. That's exactly right, because every automorphism induces a permutation on those roots, right? And conversely, if you know where all these roots go, so if you know where alpha goes, and you also know where alpha omega goes, in fact, all you need to know is really where these 2 go, then you know where omega goes. And if you know where alpha and both omega go, you know where everything goes. And so every automorphism induces a permutation on these roots, and the permutation will tell you what the automorphism does. So I'm going to see what we can do. Yeah, I wonder what the identity is. That's what the identity does for all these things. Oh, and look at me. Oh, I'm poaching the easy ones here. You guys better get on the stick. Okay, let's see if we can get an automorphism from swapping out 1 and 2. I'm going to call this phi. What happens here? Well, phi 1, 2, so I'm going to do a bunch of calculations. It should take alpha and alpha omega and swap them, right? So this should go alpha omega, and alpha omega should go to alpha. Agreed so far? Now the question is, does this work? Where does everything else go? How can I figure out where omega goes, for example? Yes.
For example, alpha square omega will go to alpha square omega too, right? Because someone.
Okay, well, let me do this one because
Ah.
it's easier for me. Alpha squared. So this goes to alpha omega, so alpha squared should go to alpha squared omega squared, right? Everybody agree? Which is alpha omega bar, alpha squared omega bar. And I am writing this as squares, aren't I?
It is bar in this case though, right?
What's that?
It is bar in this case though, like they are equal.
Yes, that is correct. I just want to be consistent since I did write alpha squares there. Where does, how can we figure out where, omega goes?
If we, that's what it's-
That is correct. So notice alpha omega goes to alpha, right? And, alpha goes to alpha omega. So if I divide this, I get omega goes to divide this. So omega should go to 1 over omega, which is omega squared. Agreed? And to finish this off, I know that alpha squared goes here and omega goes here. So this should go to alpha squared omega as well. Let me see if I'm consistent. Yep. Should put this- How about this? B13. This one, I want to swap out, these two. So I want this to go to alpha, oh, I didn't mean to say that. That's not even a root. That's alpha omega squared, not that. It should be alpha omega squared. And alpha omega squared, should go back to alpha squared. Oh, that's not on my list. So, but that's a piece that we can use. Okay, so this goes to alpha omega squared, so this goes to, where should this go? Alpha squared omega, right? This should go to alpha squared omega to the 4th, but omega cubed is 1's alpha squared omega. Okay, so far? Okay. Right, so we need to know, let's see. So what can we glean from this? We know that alpha omega squared goes to alpha. And we know that, alpha, goes to alpha omega squared. Can we get anything from this? That's right. If phi takes alpha omega squared to alpha and takes alpha, so it swaps these two out, then the quotient of this, so it should be that omega squared goes to the quotient of this, 1 over omega squared, right? Which equals. Right. So in particular, it should swap, it should just swap omega and omega squared. Everybody okay so far? Okay, so let's build the rest of it. Alpha goes to alpha omega squared, and omega goes to omega squared, so alpha omega goes to, alpha omega, so that was fixed. Right, and alpha squared omega, well, alpha squared goes here, omega goes here to its conjugate. So alpha squared omega should go to, alpha squared. Everybody understand where I'm getting? Okay. And what happens when we swap these two? In this one, we should have alpha omega. Should swap these two out. So alpha omega goes to alpha omega squared, alpha omega squared goes to alpha omega. And so that means 1 over omega goes to omega and vice versa. We do it in either order. So that means omega goes to omega squared. Right? Alpha omega goes to alpha omega squared. This goes to alpha omega. So where does alpha go? You can get alpha by taking this and dividing by this. So where does it go? Take this and divide it by this, it goes to alpha. So that goes to alpha squares too. And we all know a very familiar name for field 1, 2. What's it called? It's an automorphism that should be there. Yes.
I have a question. If we obtain the image of alpha dividing alpha squared omega by alpha omega.
Yeah, so what we did was alpha omega goes to alpha omega squared, omega goes to
Yeah.
omega squared.
Yeah, but if we do the exact same thing with the last two.
With these two.
Yep.
Well, that tells you that, yeah, you're right. This is, what's that picture? Alpha squared, omega, this should be alpha squared. Let's see. Oh, yeah, here's what I do. I copied this down, I guess. This is alpha squared omega. Yeah, I confused that with alpha omega squared, which I should have done. This is correct, and then I wrote the other one, and that's not what I meant to do. Alpha squared omega actually goes to, alpha squared omega squared. There we go. That's better. Everybody okay with that?
It's not conjugation.
This is complex, this one right here is complex conjugation. It fixes the real ones, and notice, this one's kind of a giveaway. This goes to the conjugate, but it basically conjugates the other ones, right? Okay, how about this one? What happens here? In this one, we have alpha going to alpha omega, and we do this right here, alpha omega squared, and back here. Right? So let me see what I can fill in here. This is alpha omega. And so alpha squared goes to alpha squared, omega squared, and alpha omega goes to alpha omega squared. How about omega? Where does that go?
Omega.
Looks like it goes to omega, right? We'll see alpha omega over alpha. This over this should be, yes, it's fixed. And that kind of fits my pattern here. And now that I know this, let's see, alpha squared omega, that should just go to alpha squared. And finally, it's just the inverse of this. So, oops, let's change the head to the tails like I'm doing homological alpha or something. Alpha goes to alpha omega squared, and alpha omega squared goes to alpha omega, which is alpha. So alpha goes to alpha omega squared. So the square of that should give alpha squared omega. And let's see, alpha omega goes to alpha. So I can get omega by taking this divided by this, which is this divided by this, so it goes to omega again. And this animal here should be the product of these two, which is alpha squared omega squared. Yes.
If, would omega go to omega squared? If we're dividing alpha omega by alpha?
Right, alpha omega, alpha. So this divided by this is 1 over omega squared, which is omega. And that's it. We've gone through the exhaustive list of everything possible. Notice these are all automorphisms, and that they tell you what they do to the base, the basis elements. The identity here, here's only complex conjugation, and notice that they do basically the little cycles of the roots that you expect in C6, right? Let's look at, for example, this one here. Okay, so let me ask you a question. What's the fixed field of this? What do I mean by that? What is everything in the field that is left alone by this automorphism? What does it look like?
Q alpha.
Q alpha, everybody agree? Everything else is pushed around. What about this one? What's the fixed field of this?
Q omega.
I think it's, run that by me again. I think it's probably alpha omega squared, actually. I think that this actually fixes Q adjoined with alpha omega squared. And this one fixes Q adjoined with alpha omega probably. Yes, alpha omega. What's the fixed field of this one? Both of these, the fixed field, the set of everything that's left alone is Q adjoined with omega. Right, notice it pushes the other ones around, but it leaves the omega alone. The fields, the subfields that are fixed by the automorphisms are important as well. I think it's worthwhile for me to start another example here. Everybody kind of get what's going on? If you study this, I think you'll see big chunks of the fundamental theorem of Galois theory, which admittedly I haven't even told you what it is, but I will. By the way, if you're in my class and you come to the math club today, you will see this polynomial again, but you all are not allowed to answer. You don't have to talk to. I can make, yes. Go ahead.
Because I want to ask you something about.
Oh, yes, please do.
So you said that these are all the possibilities. So how do we know exactly that all of them are actually automorphisms?
That's a good question.
Do we have to consider that the columns are a basis for the, or?
Yes, yes, the new columns will also be like a basis so yes, I haven't been very strict and formal about that, but we'll glue those pieces together. Anybody know how to find the roots of this? Because this is actually kind of easier, but maybe. It looks at first. Well, actually, they're primitive 8 roots of unity. So. Oh, right. So X is e to the I power four plus I K. And so what I get, my RIs are e to the I power four, e to the I 3 pi over 4, e to the I 5 power 4, e to the I 7 pi. Now, there's something that's soup's convenient about this. By the way, who in here is in Robert Dix's number theory club? That's what 1220? Or it's at 12, okay. I was gonna say I want to be in that class today, so I might miss some office hours, but I guess I won't because it's at 12:20. So to get all the roots of this, you have to have the smallest field containing all four of these, but I can shortcut that. Can somebody tell me how? What? I can shortcut it. I don't need to put all four of these roots in, really. I only need one of them. All right, notice that Q, I joined the tornado, what this is, e to the I power 4. This contains all four roots. Now, we'll talk about this more in depth next time, but I want to give you an example. Last time, we had the roots last time. We had 3 roots, and we had 6 automorphisms, because we went bananas and we needed them everywhere. So it's the Galois group of this, the automorphisms, is it S4? I mean, we had 3 roots before, now we have 4. Actually, I think that's. Notice this one has, you've got less freedom on this, right? In the following sense. Suppose there exists an automorphism from well, of course, there is one that takes this to this, but I want to skip that one because it's the identity. Suppose there's an automorphism that take, and as a matter of fact, there is. Well, let's take a look at this. What's another name for tornado to the 9th power?
Tornado.
That's tornado to the 8th power is 1. This should be tornado to the 12th power. What's another name for that? It's the 4th. So it's fixed. What's another name for tornado to the 4th power? Well, negative 1. Right, and I can go through all the powers. In fact, tornado. But I'll just skip some of the powers now. This is. So notice, where do the roots go? If I demand this, then the second one, so it swaps these two, and it swaps these two. You could also have tornado go to tornado 5, tornado go to tornado 7. And in fact, that first automorphism I gave you actually generates this. Okay, no, I take that back. What happens when I compose this with a cell? There we go. If you compose this, because it's swapped two pairs, if you compose this, you get the identity. You can check that all the other ones do this as well. And actually, the group of automorphisms here is Z2, Z2. Okay, any questions on that? All right. Well, you all have a good one. Hope to see you in the math club. Other than that, y'all